The stress function can also be expressed by complex functions. Before we start with this, just recall that this function phi defined before, which is equal to some function p plus iq. This is an analytic function with the property that the partial derivative of p with respect to x is equal to the partial derivative of q with respect to y. This is the first Cauchy-Riemann equation, and this should be equal to 1/4 of p, where p is the Laplacian of the stress vector u. The second Cauchy-Riemann equation takes the following form. And this is equal to 1/4 of this q, which is the harmonic conjugate of the p. Now let's take the Laplacian of the following function. U minus this function p, the harmonic function p, multiplied with x minus q multiplied with y. And it's not so easy for you to see why we are doing this, but it turns out to be very useful. So this will be the Laplacian. Of course, Laplacian is a linear operator, so this would be the Laplacian of this term minus the Laplacian of this term minus the Laplacian of this term. So what is this? Let's find the Laplacian of px. It's really trivial to do this. We have the product rule for differentiation we can use. We know that the derivative of this with respect to x is just the derivative of p with respect to x multiplied with x and plus the derivative of x with respect to p. Doing this twice in both x and y direction, we easily obtain this result. And we do the same for this Laplacian of q multiplied with y and obtain this result. Just check it for yourself that we get this result. It's really trivial to do it. It just takes some time. But note that the function p is a real part of an analytic function. So a real part of an analytic function is always harmonic, and therefore this expression must be zero. The same for the imaginary part of q. It's also an harmonic function, since this is the total function is an analytic function, so this must be zero also. So therefore we are left with a simple expression, 2 times the partial derivative of p with respect to x, and we know what this is. This is 1/4 of p, and multiplying with 2 we obtain a half p. Similarly, we obtain that the Laplacian of q y can be replaced by just 1/2 p. So we knew that the Laplacian of u was equal to p. So here we can replace this by p. We can replace this by half p and half p here. So summing up, we end up with this this expression, which is equal to 0. This means that Laplacian of this guy is 0, so what's in here is just an harmonic function. And this is now we see why it was interesting to find the Laplacian of this expression. So we call this function for p1. We call this function p1, and if this is equal to P1, then U must be equal to this sum of functions. We can also denote some other function Q1 to be the harmonic conjugate of this P1, and then we obtain an analytic function, or if you like, the complex potential corresponding to P1. And we observe the following. We observe that if we multiply the conjugate of set by phi plus this function, we obtain the following. We know that set is just x plus iy, and the conjugate of this is this expression. We know that this phi is we have already seen that this function is equal to p plus iq, so we obtain this, and recently we defined this function chi by this expression. So now we can take the product of these two, and we separate the terms which are purely real, and we collect also the terms which are purely imaginary, and we obtain that the real part of this is equal to this expression, and the imaginary part is equal to this expression. So now we see that U is just equal to this real part of this expression, which is this term. So just recall that we already had said that U, capital U, is equal to this expression. So now we identify this expression as the real part of this function. So that's the reason why we now have an expression for this stress function as the real part of this complex function. Now, just recall, we have seen this many times before, but just recall that if set is equal to x plus iy, then the sum of set plus the conjugate of set is equal to 2x. It's really trivial to see. So this implies that the real 2 times the real part of set, because x is the real part of set, is equal to set plus the conjugate of set. So using the same method on this expression, which is taking the real part of this is equal to u, we obtain that 2u is equal to this guy plus its conjugate. So it's also simple to see that this turns out to be the conjugate of set multiplied with phi of set plus these terms. By differentiating with respect to x and y, we obtain, and this is not so very easy to see, but it takes time to see this, that the derivative of u with respect to x is given by this expression. Similar, that 2 times the derivative of the stress function with respect to y is equal to this expression. So the function defined by the derivative of u with respect to x as real part, and the derivative of u with respect to y in the imaginary part, this function, by adding these 2 terms here we must multiply with I on both sides, we obtain this result. That's because several of these terms are cancelling each other. Now we have an expression for the stress function in terms of a real part of a complex function. And this complex function is given by phi and chi, and we have proven that such functions exists. Such function exist, and a natural question to ask is, what happens if these two functions was any arbitrary function? Arbitrary function, analytic function phi, and an arbitrary function chi. Would this expression then give us that this stress function u is satisfying the biharmonic equation? And the answer is that yes, this would lead to an function which is a stress function which satisfies this biharmonic equation. So let's just sum up what this video was about. The biharmonic function can always be written in the form u equal to the real part of this complex function, where phi and chi are analytic functions. On the other hand, for all analytic functions of this type, we have that this function defined by the real part of this complex function turns out to be biharmonic.